He's walking in a few minutes.
Great. Hello, I'm AJ. Can you hear me? Awesome. Okay, so yeah, reviewing induction, because induction is going to be plaguing you forever. It's important for your CS career. It's important for your career in life. It's important for everything. So induction, logically what it's saying is that if you want to prove something for all n, some proposition, that's completely and utterly equivalent to, or well, for all natural n, I guess. If you want to prove something for all natural numbers n, that's completely equivalent to saying it works for the first case, and that every case implies the next case. Okay? That's what induction is saying logically. It's like the domino effect. You prove the first thing, and then every other domino falls right after that. And I think we were getting into, especially in discussion, we were trying to get into strong induction and strengthening the inductive hypothesis. These are kind of twists to induction that we'll need to use because induction, it comes in many flavors, it comes in many forms, and we're going to have to be using all of them if we want to get some lots of proofs out of this course. So, strong induction, we realize that induction, you assume the first case, or you assume one case and you try to prove the next case. But that's not exactly how induction works, right? Because if you're already on the kth case, it means you've proved everything up until that point. So if you're trying to prove P of 6, assuming P of 5, you probably also prove P of 4, P of 3, P of 2, and P of 0, right? So you could actually assume everything up until that point. So strong induction is saying P of 0 and for all j less than k, P of j implies P of k plus 1. So, strong induction. You not only can you just assume the case right before it, you could assume every case before that one, and maybe that'll help you. So instead of just saying P of k will help you prove P of k plus 1, you could use P of k over 2, P of k minus 5, P of k minus 10. Every case before the one you assumed, you could also assume, and then prove the next case. And this is a property of induction because we built it up from the first case, from P of 0. And Umesh is back.
Could you go in there and get me a white and yellow chalk?
Yeah, sure.
In the back. Okay. Hi. All right. So, thank you. Thanks a lot. Yeah. Okay. Great. Okay. So, here's the plan for today. We're going to first start talking about some other properties of induction. Okay. We're going to cover a couple of aspects of induction. One is the fact that you have to be careful with induction, right? It's a powerful argument. You go wrong somewhere, and then your errors don't stay local; they just propagate everywhere. Okay, so I'll show you an example of that, and then we'll look at one other property of induction, which is sort of extraordinary. So let's say you're trying to prove something by induction, and you're having trouble doing it. You try, and it's just too hard. So normally, you're trying to do something like that, and you think to yourself, I can't really solve this task. Let me try something simpler. In the case of induction, sometimes it helps to think the other way. You say to yourself, I can't solve this problem. It's just too hard. Let me try to prove something harder. Something more general, right? And suddenly it becomes much easier to do. Okay? And then what we'll do is we'll step back and we'll look at induction from an axiomatic point of view. Right? So many of you have this, I think some of you articulated this question, well, what exactly do we mean by proof? When do we know it's a proof, and how much detail, and so on? So we'll go back and examine this question in the context of induction right from first principles and say, where does it come from the axioms? What are we really trying to do? Okay? So that's the... Oh, sorry, I forgot to mention, that's the first half of the lecture. And then the second half, we'll talk about induction and recursion, if we get there. Okay? So here's... okay, so this first example is about how things go wrong in induction. And when little things go wrong, sort of a little error can propagate everywhere. So this is an example due to George Polya. Who was he was a very famous mathematician, but even more than that, he was a famous popularizer of mathematics. He wrote a book called How to Solve It. And so he was very interested in how you teach mathematics. And his view was mathematics is taught extremely poorly because it should be something that makes you think rather than memorize or, And so this book, How to Solve It, is about some kids who are working on mathematics together with a teacher. And what they're doing is completely different from how a normal classroom works. Well, maybe it's closer to how a classroom works today than it did then, but even so, it was so radical in terms of how these students were trying to discover mathematics rather than just imbibe it. Okay, so it was about problem solving, about what kind of strategies you use, and one of the kids was very good at problem solving, and another didn't seem to be. And then when it got to conceptualization, she was extraordinary at it. And so each of them had their strengths, and there are all these different parts of mathematics and different aspects to it. It's a beautiful book. So anyway, this particular example is by Polya. It's a takeoff on a saying from long ago, I think from the 19th century, where if you came across something sort of extraordinary or different from the norm, you would say something like, "That's a horse of a different color." Okay, it's just a saying. So here's a theorem: all horses have the same color. Okay? So proof by induction. On n, the number of horses. Okay, so let's start gentle, right? So let's start with n equal to 0, n equal to 1, base case. So non-empty sets, right? So n equal to 1. Any set of one horse, well, it's obviously the same color as itself, so it's trivial. Induction hypothesis. Any set of k horses. In any set of k horses, all k horses must have the same color. Okay. Induction step. So let's look at a set of k plus 1 horses. So you have an S set of k plus 1 horses. Let's show that they're all the same color. Okay, so what do? We look at the first k horses. By the induction hypothesis, they're all the same color. Then we look at the last k horses. By the induction hypothesis, they're all the same color. So now, think of it this way. You have these horses are all lined up. You have two windows you can look through. Right? You can open either the first window or the second window. You can open the window from this side, and you see the first k horses. And indeed, all k are the same color. Let's say that you can't see the color itself. Okay, can you imagine that? You open the window, you see that they're all the same color, but you have no idea what the color is. How could you do that? Well, every time you open the window, somebody changes the lights. Okay? So now you just see some strange color in there. Right? The horses are actually brown, you see purple. Okay? Because of the way it's lit up. But you can still tell that they're all the same color. You have no idea what color they are. You can see that they're all the same color. You go back, you open up this window, you see all these are the same color. You have no idea what color it is. So you can't say, oh, by the way, I saw all these were brown. When I opened this, they're all brown. It's the same color. No, there's no such thing. Each time you open the window, different color. Okay, but now you can reason like this. You can say, look, these middle horses, no matter which side you view them from, every time you open them, right? These are horses, right? They're not chameleons. Whatever color they were, they stayed the same color. So we know that these horses are the same color as the first one from this side. We know that they are the same color as this one from this side. Right? So therefore we know this must be the same as these, must be the same as that. Right? Because when we saw these two together, they were the same color. Always, which means these are really the same color. When we saw these together, we saw they're the same color, always, so they are the same color. So all of them must be the same color, which implies all same color. So we are done by induction. All the colors you see around you is just illusion. We proved it. Okay? So where's the flaw in the proof? Yeah, very good. Okay, so is everyone ready for the answer? It was the right answer. Most of you didn't hear it, but if you want to keep thinking, are you ready? Okay, whatever you're tempted to do, don't say that the proof is false because the induction hypothesis is false. That never comes into it. In a proof by induction, we never, ever, ever said the induction hypothesis has to be true. Right? We are trying to prove it's true, but we assume it's true. Right? So if induction works, you can't say, well, we happen to know this is false, therefore the proof is wrong. No, that's not true. The proof is all about, the proof says, prove the base case, assume this, from that derive this, and you're done, right? You don't have to worry about whether it was true or not. You've proved it's true, right? So now the flaw cannot be that it's false. The flaw is in the procedure somewhere, right? So something went wrong in the proof. The fact that we got to, prove something false, it has to do with the proof. Okay? So what went wrong is this drawing is misleading, right? Look at the case where k equal to 1. That was our base case. We proved it. This was a true statement. K equal to 1 horse. That's good. We are now trying to show for 2 horses. So this is 1. K plus 1 is 2. There are no middle horses. Right? Here's another way to say it. We were this close to proving that there are no colors possible in the world. if we had just got past that case, everything would have been fine from there on out. Right? The rest of the argument was completely correct. There was just that one case that went wrong, and then that got us into all this trouble. Right? So what happened here is that the base case n equal to 1, this was true. Then we were trying to create a set of implications, 2, 3, 4, 5, so on. Right? So we wanted to go, this implies, this implies, this implies, this implies, so on. Right? That's how you do induction. We inserted an error in there somewhere. That was this. Right? The second one was false. This is where we made an error. But now, once we put in false anywhere, that implies anything. Right? False implies false. So from then on, everything goes wrong. Yes?
What if you say, what if you prove two base cases? Or, let's say in the theorem that you say if two horses are the same color, then all horses have the same color.
If every set of two horses have the same color, then all horses. That would be a true theorem. That would be a true statement. And in fact, this is a proof of that. Very good. So what we actually proved was what you just said.
I'm just saying that two horses have the same color.
If every set of two horses have the same color.
Not every set. I'm just saying two horses have the same color.
Well, then you're out of luck.
Because the main flaw with this is that there's no middle or two, right? So if you say that we can prove that one and two horses.
Well, then if you prove that every set of one and every set of two horses have the same color, then it follows that every set of n horses have the same color. That's what this proof is really showing. Yeah?
What if we start with base case 3 horses?
Well, if you happen to be able to prove that statement, then you'd be golden. Then it would all be true. We missed it by just one case. It's a lucky thing we missed it. So it would be a boring world if we had not. So, yeah. Well, what about if you took one from each? Then it wouldn't be a... Yeah? Yes?
Is this proof just there to illustrate the inalienability of induction, or for the purposes of this class, we need to worry about cases in between K and the base case where the argument might be fairly?
I'm sorry, I didn't catch your question.
What I'm saying is that for the purposes of this class, do we have to worry about cases in between the base case and our assumption K?
Well, for this class, you have to worry about whether something is correct, which means you have to worry about everything. Yes? Yes?
Say we change base case to 3, and it is true, but we know there are forces other than...
Well, then your base case is not true. Yeah? Okay, by the way, this whole idea that false implies anything. There's a great story about Bertrand Russell, who was a great logician, who, he was trying to put mathematics on a completely solid basis about 100 years ago. And he thought he had achieved this remarkable goal. Russell and Whitehead, they published their great tome about this. And they were having a press conference. And in this press conference, some of the reporters got very intrigued by this whole notion that once you get a contradiction in your mathematical system, once you get a contradiction, you can prove anything. The way Bertrand Russell had said it in his while explaining to them is, he said, as soon as you have a contradiction, for example, if I ever prove 1 equal to 2, then I can prove anything I want. I could prove I'm the Pope. And so one of the reporters said, how would you do that? Can you show me? And this is a nightmare of somebody a mathematician or a scientist who is talking to somebody in the press, because you say something and And, it's obvious to you, but then they ask you why, and of course the answer is so technical. You think to yourself, implication and truth tables and false implies anything. How do you tell that to a reporter? But Bertrand Russell didn't miss a beat. He said, consider a set with two people, me and the Pope. Yeah? Okay. No? Yes. No, it was a joke. So I don't know if you know the story about Richard Feynman when he was visiting China, and he was speaking, and he had a translator who did a wonderful job translating his lecture into Chinese, and then Feynman in his lectures would tell jokes, and he was surprised. Every time he told a joke, the audience would laugh politely, uproariously, whatever. It was extremely impressive. And then he was sure that there was one joke he told where he was sure nobody would, it couldn't possibly be translated. But sure enough, after the translation, everybody laughed. So afterward, he asked his host. He said, "Well, that translator, amazing. I was really surprised he translated that joke." And his host said, actually, what he was saying was, "Professor says joke." So. Okay, so let's talk about. Okay, so let's talk about the second thing I said we talk about, which is this notion that you're trying to prove something, it's too difficult to do, and so you double down and prove something even harder. Okay, so let's say we are proving the statement. By the way, this is something that's particularly notable about induction. So we'll come back and see why it is, why it makes sense that in the case of induction, this might happen. Okay? So if you start from 1 and you start summing up consecutive odd numbers, the claim is you always get a perfect square. Right? Sum of first n odd numbers is a perfect square. Perfect square, you know what that means, right? Like k squared, like 4 squared, which is 16, or 5 squared, which is 25, right? So it's a square of a natural number. Okay? Proof by induction. On n. So base case, n equal to 1. So what's the sum of the first odd number, which is 1, right? So 1 is a perfect square. Induction hypothesis. The sum of the first n odd numbers. So 1 plus 3 plus. Okay, for the first k, so 2 times k minus 1 plus 1, right? So this is 2 times 0 plus 1, 2 times 1 plus 1, 2 times k minus 1 plus 1, right? So that's the kth odd number. So we're claiming that this is a perfect square. This is of the form m squared for some some natural number m. Right? That's our assumption. It's a perfect square. And now we want to show induction step. So now we want to look at 1 plus 3 plus dot 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 plus 2 times k minus 1 plus 1 plus 2 times k plus 1. We want to show this is a perfect square. Okay, so what do? Well, clear, right? We are doing induction, so we take this and use the induction hypothesis. What else can we do? I mean, that's all we can do. So we get m squared plus 2k plus 1. We want to say m squared plus 2k plus 1 is a perfect square. That's nonsense, right? How could you ever conclude that's a perfect square? There's no relationship between, I mean, what do we know about m versus k? Why should this be a perfect square? Right? Okay, so obviously this is too hard. We can't possibly solve this by induction. Right? So now what do? Well, let's try to solve something harder. Let's prove something more. So at this point, when you're doing induction, you say to yourself, look, don't waste my time telling me just to prove that it's a perfect square. I mean, this is too little. Give me a bigger task, and I'll solve that. Tell me to prove more than that. Not just that it's a perfect square, but it's a perfect square with some property, something even more specific, something which after I prove, it'll be obvious that it's a perfect square, because it's a perfect square as well as it satisfies some other property. Okay? So obviously it's a harder task to do, because what we're offering to do is not only do this, but also do something else in the process. Right? But we are saying it'll be easier to do both simultaneously. Okay, and to do that, to figure out what that something is, let's work with some examples. So let's work with some examples. So let's figure out what's the sum of the first odd number is equal to 1. The sum of the first two is 4, which is 2 squared. 1 plus 3 plus 5 is 8, which is 1 plus 3, 9. 3 squared. 1 plus 3 plus 5 plus 7 is 16, which is 4 squared. 1 plus 3 plus 5 plus 7 plus 9 is 25, which is 5 squared. That's extraordinary, isn't it? I mean, that's amazing. The sum of the first n odd numbers is just n squared. It's not just any old perfect squared, it's n squared. Okay? So let's prove that. Okay? So naively, you would think we are being asked to prove more, right? Before we were just being told to prove it's a perfect square. Now we're being asked to prove not only is it a perfect square, but it's actually n squared. How do we know that we're being asked to prove more? Because after you're done proving that it's n squared, you could just step back and say, by the way, it follows that it's a perfect square, because n squared is a perfect square. It's trivial, right? So the previous conclusion follows from this one, easily. We are doing more. Yes? Oh, yeah. Yes. And that's what we are doing here, right? Yeah? Yes. Yes, very good. Yeah. Okay, so now the theorem that we are proving is the sum of the first n odd numbers is n squared. Okay, that's the theorem we're proving. By induction, base case, so again, induction on n, so that's our proof. By induction on n, base case 1 equal to 1 squared. Induction hypothesis 1 plus 3 plus dot 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 plus 2k minus 1 plus 1 is now equal to k squared. the step 1 plus 3 plus dot 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 plus 2k minus 1, 2 times k minus 1 plus 1 plus 2k plus 1. So now we say, look, by the induction hypothesis, these first k terms sum up to k squared. And lo and behold, we have k squared plus 2k plus 1, which is equal to k plus 1 whole squared. And we are done. Right? Okay. This is a particularly nice example. It's in your notes. Okay? It's a particularly nice example because it's so simple. Right? And you can see it. It's completely transparent. You see where we use the extra information. You know, in what sense we are making the task harder in the sense that we are proving more. But that by making it harder, we're also getting an assist in proving the next step. Here's one way to look at it. Remember our dominoes? And that's induction, right? You're knocking over dominoes. In terms of dominoes, what does it mean we are trying to solve a harder problem? We are trying to reach farther with each domino. So maybe, to make this problem harder, maybe I take this domino and move it up here. And that became a bit harder to, because now this domino had better reach across and knock that one over. It's harder for it to do that. Okay? Why did it become easier? Okay? It became harder, right? But also, why did it become easier in the same breath? It got closer to the next one. Right? You moved this forward, but now the next one, maybe the next one before was out here. It was just out of reach of this one. Right? Where it used to be, it would fall down and would just miss it. But now we moved it up, and now it reaches there. But maybe in the process of moving it up, this one was tall enough that it would actually reach it. So it's a placement of dominoes, right? You've got to make sure that you're placing them right so that you can get to the next one, and then, moreover, the next one is far enough along that it gets closer to the following one, right? It's a matter of placing the dominoes right. Over here, we just didn't place them very well. And so you move it along a little further. And now you're just far enough to reach the next one. Okay? Yeah.
Maybe it's obvious, and I'm just missing it, but why is it 2k minus 1 plus 1? And how did you think of that?
Oh, how did I think of it? What's an odd number? It's of the form 2 times something plus 1. What's the first odd number? 1. What is it? 2 times what plus 1? 0. What's the second odd number? 2 times 1 plus 1. Right? So the second one, you do 2 times 1 plus 1. So for the kth one, you do 2 times k minus 1 plus 1. Yes. Yes.
How do you justify it in sort of like a general sense that allows you to make that assumption?
That it's k squared? Oh, you just have an intuition that it is, right? So remember, when you prove things, no. So what you're trying to do in mathematics, what you're trying to do is you're trying to understand the world, right? You're trying to understand. You're trying to understand what's true. So how do you get at what's true? Well, first you start with your intuition about what's true, right? Because if you're just sort of looking around in the dark, that's not a very good thing. So you have some beliefs about what's true. So and the beliefs are based on examples. It's based on other things, the pictures. There are many ways you can come to these beliefs. And then you want to understand, is it really true? What does it take to really pin it down and say, this is true? I'm completely convinced about it. Well, that's what this is trying to do. Right? So far, when we said, this is what we are trying to prove, well, this is our hope that we'll prove it. We think it's true. After we are done with this proof, we know it's true. Right? Because we verified it step by step. Okay? Actually, let me get to this in two ways. Okay? Let's try something. Okay? So one thing. Okay. So how do we know it's true? Okay. The proof is not necessarily how you discover these facts. You discover them by doing small examples, but then there's also, instead of proving it by induction, you could also prove it by picture in this case. Okay? Here's how you could prove this. The sum of the first n odd numbers is a perfect square, is n squared. Here's the first odd number, 1. Here's the second odd number, 1, 2, 3. Okay? Here's the third odd number, 1, 2, 3, 4, 5. Fourth odd number. Okay? Okay? So you should be aware of this, that proofs are not all there is to it. There's pictures as well. And pictures are extraordinarily powerful. Right? You should be thinking in pictures wherever possible. By the way, there are two kinds of people. There are two kinds of among mathematicians, there are two kinds of people, but also, in general, there's the picture people and there are the language people. Right? There are people who think in language, there are people who think in pictures. Well, of course, there's a spectrum, right? It's not that it's so stark. People think in both. But every so often you come across somebody who just thinks in pictures, or somebody who just thinks in language. And there are different fields of mathematics which are picture-oriented, and there are different fields which are language-oriented. Right? And you have to pick what's your forte? Right? Yeah.
Speaking of pictures, did you ever figure out that chocolate bar proof?
Yes, I was going to cover it, but if we get through everything else, then I'll cover it. If not, I'll find a place to insert it. Okay? Yeah. Okay. So now, okay, well, there's the picture aspect of it. Now let's go back and look at the proof aspect. So what are we doing when we are doing a proof by induction? So what I'm going to do now is I'm sort of going to go behind the scenes and show you where an induction proof comes from. What are we really thinking when we do a proof? Okay? So to do that, we are going to go back and look at what do we know about the natural numbers? Well, how do we know what the natural numbers are? Well, the answer is probably many happy hours spent in your kindergarten playing with little pebbles. Right? That's when you understood what natural numbers were. You developed a picture for them. You developed the circuits which, in your mind, which sort of understand, picture, whatever. What are numbers? Okay. But then, if you are trying to get at the ultimate truth, what's really true. Do you trust all that play that you did in kindergarten? Right? Yes? Good answer. That's a good man. It's a secret to success in life. Actually, it is. You should trust what you did in kindergarten. But having done that, if you really do want to get to, this kind of metaphysical certainty, how do you get there? Okay. So the way you get there is you codify and you say, this is what I know about the natural numbers and nothing more. So in other words, what you do is you separate out your pictures and you say, that's how I'll think about it in my private time. And those are my beliefs. Right? That's how I discover what's true for me. But then, when I'm proving something, I put that aside, and I don't consult it. All I consult is this very precise conception of what the natural numbers are. What's this very precise formulation? It's called Peano's axioms. Okay. Axioms. Axioms are statements we accept without questioning. Okay? So in other words, instead of relying on what we learned in kindergarten and accepting that without questioning, which is fine, it's fine to do that, except we don't remember. We don't remember everything we accepted there without questioning. So we sort of codify this, and we say, this, we'll precisely state exactly what we are going to accept without questioning. And this is the only thing we'll accept without questioning about the natural numbers. So that when we are proving something about the natural numbers, it has got to follow from just these statements alone and the rules of logic. Right? That's all that we can invoke. And everything that we derive is going to be this sequence of implications, little implications, where each implication we can see. We can say, well, this follows because that statement was an axiom. This we already proved. When you put the two together using this logical deduction rule, this one follows. Right? That's what we're doing. That's what a proof is. Okay? So what are these axioms? Axioms say 0 is a natural number. It's just a symbol. Okay? This is language. Okay? No pictures here. 0 is a natural number. For all n belonging to n. So if n is a natural number, there's this function called the successor function. Okay? S of n is a natural number. Not equal to n. Right? S of n is not equal to n. It's a distinct number. Okay? Behind the scenes, okay, this is happening in axiom land. From the side we are looking on, because with all our pictures, and we are saying, really what that means is n plus 1. For every number n, there's an n plus 1. Okay? But we are not allowed to know this because we don't have any pictures. Right? This is just the very basics. We are being very cagey about this. These are the only things we know about the natural numbers. 3. If for all m, n, m is not equal to n implies S of m is not equal to S of m. Okay? You can't get collisions, right? If you are sitting here in picture land, we are saying, well, when you add 1 to 2 different numbers, you get different numbers. Right? The only way you get the same number when you add 1 is if you add it to the same number. Right? I guess the way this is usually stated is a contrapositive. Okay? Shall I state it as a contrapositive? This is not how it's usually stated. Okay. The way it's usually stated is if S of m equal to S of n, then m equal to n. The only way you can hit the same value is if you start from the same thing. 4. There does not exist n. Okay. Nothing. 0 is the successor of nothing. Right? We do not have -1 among the integers. Picture land, right? But that's the other axiom. Okay, so far, what do we know about the natural numbers? Well, if you were to draw a picture of it, what we know is that there's 0, and then there's something called S of 0, and then there's something called S of 0, and there's something called S of S of S of 0, and so on. Yeah? That's all we have, right? We have 0, and then we can get a successor to it, and then we can get the successor to the successor, and that's the successor to this is S of that, and then the successor to this is S of that. What's S? It's just add 1, right? So it's 0, 0 plus 1, 0 plus 1 plus 1, 0 plus 1 plus 1 plus 1, and so on. The fact that we name them something else, that's our issue, right? It's as far as the objects are concerned, this is the property that we have. And then the last axiom is called the induction axiom. The induction axiom, so give me a moment. If it's an essential question, yes. Yeah. Oh, yeah, you're right. Yes, of course. Sorry. Oh, sorry. No, sorry. It's not equal to, it should be, there does not exist M. So, yeah, thanks for asking, yeah. Okay, so, it should be saying, there does not exist a natural number whose successor is 0. So there's nothing to the left of this. Right? Okay. Yes? We are not defining it. We are just saying there is this function. It's just there. And then we interpret it. We'll call S of 0, we'll call it a name, which is 1.
One more thing. Wasn't 0 not included at one point in the natural numbers?
At one point, meaning historically?
Yeah.
I don't know. Yeah. People have all kinds of confusion about it. Some do, some don't. When you're axiomatizing it, you always do. Yeah? Okay. The last axiom is the induction axiom. Yes? I'm sorry? I'm sorry? On 4, yeah? Should there always be successor after 0? I don't understand what you mean. No? Okay, sorry. No, this is saying there cannot be any natural number whose successor is 0. Right? Successor means something, it's saying there's no natural number such that when you add 1 to it, you get 0. Right? Because that's minus 1. It's not a natural number. Okay. And then there's the last axiom, which is the induction axiom. What does the induction axiom say? It says, look, these are the only natural numbers there are. If you write them out like this, 0, S of 0, S of S of 0, and so on, that's it. There's nothing else. Okay? And how do you express the statement? Well, the way it's expressed is by saying, suppose you have some set S. K. Let's suppose that there's some set K. Suppose that there's some set K such that 0 belongs to K. And for all n belonging to K, whenever n belongs to K, S of n belongs to K. Then K contains n. Then K contains already all the natural numbers. Okay? What's this telling us? It's saying, look, as soon as you got 0 and all its successors, you already got all the natural numbers. In the set K, you might have other things as well. You could throw in -1 as well. You could throw in other numbers. That's fine. As soon as you include 0, and as soon as for every natural number you include its successor, you've already included all the natural numbers. Okay? You see why that's called the induction axiom? Because that's what we are doing here. We are saying for which values of n does this statement hold? Call that set of n. Let k be the set of n such that the sum of first n odd numbers is n squared. Okay? Here's a set k. What are we doing? What are we showing about k in this proof? Well, what we are saying is base case 0 is an element of k. Right? Induction hypothesis, induction step. What is that saying? It's saying, okay, this is capital K. Right? That's little k there. So induction hypothesis / step. What is it saying? It's saying if, let me do the induction hypothesis with n instead of k, because I don't want confusion here. So what it's saying is if n belongs to this set k, meaning if the statement holds for a certain value of n, right? If n belongs to this set k, then n plus 1 also belongs to k. Right? That's an induction step. And now what we're saying is this implies that n, all the natural numbers are a subset of k, meaning that the statement holds for every natural number. Right? It's just the induction axiom. Okay? So this is what we are doing behind the scenes. Okay? Don't worry if you didn't understand this. It's okay. You don't have to understand this. But for some of you, I hope this makes it clear why, for some of you it's really important to understand why we are doing something. And once you see why we are doing something, everything else falls into place. So for those of you, look at this. If you're not inclined in that direction, just pretend this didn't happen. Okay? Okay, so just to finish the thought. Okay, so what we are doing when we are writing down these proofs is we are putting ourselves in this special frame of mind where we say, look, we have all these intuitions, we have all these pictures about the natural numbers. They are wonderful and they provide us many insights, but we are going to take those and we are going to put them aside. And then we are going to go to our tools, which is these axioms. And that's all, for our purposes, that's the only properties of the natural numbers that we know. Okay? So now we are down to just machine language. Right? All these high-level constructs we built up, pictures, no graphic interface. We are down to just the machine language itself. Because that we are sure about. We know who programmed it. We are starting from scratch. There might be bugs everywhere else. Okay? And so we start with this, and then induction happens to be the most powerful of these axioms. It's sort of telling us what the integers look like. Well, the fact that the integers just look like this, they stretch out in a line, this is the content of the induction axiom. So if you want, one way to think about it is somewhere when you're doing your proof, you have to tell your proof that your conception of the natural numbers is that they stretch out in this line, in this discrete fashion. Where do you tell your proof that? After all, your proof didn't grow up in kindergarten playing with little pebbles. Well, this is how you tell it. And that's the induction axiom. Okay, so it's a purely mechanical way, something that you're completely certain of. We pin down exactly what our assumptions were about the natural numbers. No pictures allowed. And then we have perfect certainty. These are the things we can be completely certain about. Okay, that's your proof. Okay. Now, as I said, a proof in real life is a negotiation. It's a social negotiation, because if you do proofs this way, you might be certain of everything, but you won't have any friends left. Right? It's very tiring to do proofs this way. And so you make allowances for other people, and you say, look, we've gone through this many times together. We understand this piece. Can we just agree between us that there's no problems here in this part of the proof? Let's just be adults. We have a picture. We'll if you look inside the picture, it's all going to work out. This part of it, I'm really not sure about, so let's muck around in the, at assembly code level. This one I'm more sure about. We'll do it in a high-level language. Yeah? So you do this sort of negotiation where you sort of say, you expand some pieces out, and you look right at the core, and you say, I'm really not sure about my ground here, and so I need to open everything up. These parts I'm pretty confident about, so I'm just going to rely on the graphic user interface, and everything's going to turn out fine. Later, if somebody challenges me, I can pull it apart, and I can sort of say, how did I go from the graphic user interface to this language to that, so on. Okay, step my way down. Okay, does it make sense? Yes.
For the third axiom, if you define n equals n plus 2, we get a set of all even numbers, but n naturally is not a subset of them. But so that n is not a subset of them.
Well, you'd have something isomorphic. We can talk about this afterwards. I think you're yeah. Okay. Oh, you're right. Okay, so we have to do one other thing. Okay, so yeah, good point. Okay, so any questions? Actually, let's take a moment also to ask, any questions about the class generally, logistics or anything else while we're at it? Yes?
That homework rubric.
Yes.
Is there a formal rubric for it?
Is there a formal rubric? Say a little more. What would you like?
If you get, so if it has this many parts and you get this many ranks, then you assign it to this value.
Oh, I see. So the idea is, okay, let me just say what the rationale is with the grading, and so there are two things. What you're supposed to do with the grading is understand the solution, right? You're supposed to understand the solution and then see how far did you get. And basically we are using a digital abstraction here. We are saying grading is not, it's not on a, it's not, you don't assign yourself a real number between 0 and 1, it's just a few points. And there are a few meaningful points for us. The few meaningful points are, did you either get it correct, completely correct? Did you come very close to getting it correct? Did you get it completely wrong? Were you very close to getting it completely wrong? Or were you somewhere in the middle? And that's all we want you to figure out. Okay? Now, the exact details, did you get 5 things right here and 4 things right there? I mean, these are not such complicated questions. So, you either got it or you didn't get it, and you were pretty close. You hardly got started, or you were somewhere in the middle. You were sort of blundering about, but you didn't quite make it. Okay, and that's the level of granularity you're grading at. And quite frankly, I don't know if there's much more information to be had there. Yeah.
So, how rigid are the solutions? Are there other options?
Oh, there are other options. So, by the way, in the solutions, we are also trying to explain to you, right? So we are going a little bit beyond what you are supposed to do, or we are trying to make it as clear as possible. So hopefully this will work itself out, and if you keep the lines of communication open, we'll sort of converge onto something that works for you, and where we can try to help you as much as possible.
So what I meant, for example, so if the solution gives you a proof by contradiction,
yes.
Say proof by cases.
Yes, so that's fine, and sometimes there'll be a completely different way of solving something, in which case you can just highlight it, and you can say, by the way, I think what I wrote is correct. It's a completely different proof. Here's what I'm assigning it. You can even maybe we can find a way of actually having you highlight that and say okay, this is what I'm doing, and then we'll have a reader look at it, and if you're off, there's no harm, no foul. Okay, let me see if we can implement that system so that okay.
So is it piano?
Piano, yeah.
So piano's axioms, so they're essentially, are they just a way to like formalize the common sense behind proof logic into formal math logic?
It's just it's just doing this. It's taking the natural numbers and it's saying what are they, right? And it's writing out, So in other words, in mathematics now the natural numbers are an undefined object. We didn't define it. All we did was we said, here are some constraints that they satisfy. These are the axioms. And now the natural numbers are anything that satisfies these axioms. Yeah? So we may have many, many different models for the natural numbers, and that's, yeah. I'm sorry, I don't remember the numbers of the nodes. I think induction is node 2. Is it node 2? Node 3. Node 3. Okay. So that's how far we are going. Yeah? But sorry. I don't remember the upcoming homework. Did we have a stable marriage problem or not? No, so far. Okay. So do we? No. Okay. Good. So we are confined to node number 3. I think node number 2 and 3 for this homework. Okay, so let's talk a little bit about induction and recursion. I'm sure all of you know about the Fibonacci numbers. So they're defined like this. Excuse me, sorry. Can we? Okay. Okay, everybody. Okay, so 15 more minutes. Let's just focus for 15 minutes. Okay, so Fibonacci numbers. So the way they're defined is, say f of 0 equal to 0, f of 1 equal to 1. And then from there on, what you do is you define the next Fibonacci number to be the sum of the previous two. F of 2 equal to 1, sum of these two. F of 3 equal to 2. F of 4 equal to 3. F of 5 equal to 5. 6 equal to 8. Let's keep going for a little bit and just see. F of 7 equal to 13. F of 8 equal to 21. Okay, so the obvious thing once you start calculating it is that they start growing pretty fast. Initially it sort of just stays, it doesn't seem clear what it's doing, and maybe it's increasing by 1 each time or something, but then by the time you're in here, you're getting pretty close to, you're increasing pretty fast at a pretty fast clip. Now, if you write out how the Fibonacci numbers are defined, it's clear they're being defined by, it's a recursive definition, right? Because what are we saying? We're saying f of 0 equal to 0, f of 1 equal to 1, and f of n plus 2 equal to f of n plus 1 plus f of n. That's not good form, right? Let's write it differently. F of n equal to f of n minus 1 plus f of n minus 2 for n greater than or equal to 2. Right? So we are defining f of n in terms of sort of previously defined values of it. Right? We are sort of saying, if you want to know what f of n is, it's perfectly well defined, but in terms of smaller values of f. So it's a recursive definition. So now the thing to notice about recursion is that recursion really, recursion and induction are, they're like peanut butter and jelly. They just go together. There's, you have one, you need the other. Right? It's just no good without the other. Okay, so let's see why that works out. You'll see this time after time, and in fact, you'll also probably see. We'll do this in the homeworks. You'll work through recursive algorithms and proofs by induction that analyze those algorithms. And you'll start seeing that if you did not understand recursion before, when you studied it in 61A, you start understanding it now because you start understanding it. Well, because to understand it, you were missing an ingredient, which was induction. And if you did understand it in 61A, hopefully you will now understand it at a deeper level. So do try to do that. Right? And so I'll do sort of very simple examples here, but then as we go through, in the homeworks, you'll be doing more and more elaborate examples. And, well, these are elaborate, but conceptually, there's nothing complicated about the examples. Right? You can carry them around in your head, and you can be going for a walk, and you could be thinking about it. You don't need a paper and pencil. It's just that your mind needs to stretch in some way. So that's what we're trying to do. Okay, so let's show that the Fibonacci numbers grow very fast. So how fast? Exponentially fast. So maybe you want to show that f of n is at least f of yeah, 2 raised to the power of n minus 1 over 2. Okay. Everyone seen this little thing here? Does everyone know what that means? Floor, right? What's the floor of 2.05? Just 2. Right? You just leave off the fractions. Yeah? So if it's 2.5, floor of that is just 2. Yeah? So it's at least n minus 1 over 2. How would we prove this? Oh. Let's assume n is at least 1. Right? We don't want to get to negative 1. I don't know what happens there. Actually, it works for negative 1, does it? But let's play it safe. Let's say for n greater than or equal to 1. I'm sure it might even hold for n equal to 0, but let's play it safe. So, proof by induction on n. So base case. So remember what we're trying to do. We are trying to understand how recursion and induction sort of play off of each other. So we'll sort of work our way through. Okay, so what do I want to do here? What I want to do is I want to say, look, here's n. 1, 2, 3, 4. Here's n minus 1 over 2 floor. Okay, what's 1 minus 1 over 2 floor? 1 minus 1 is 0, so you get 0. 2 minus 1 over 2 floor. 2 minus 1 over 2 is 1 over 2 floor. We get 0 again, right? 3 minus 1 over 2. We get 2 over 2 floor. That's 1. So we get 1. 4 minus 1 over 2. That's 3 over 2, which is 1.5. Take the floor, we get 1 again. So what would you guess 5 and 6 gives us? 2 and 2. 7 and 8 gives us. So somehow what we want to do in our induction is we want to take them in twos. This is where the exponent is 0, here's 1, here's 2, here's 3, and so on. So what we're going to do is we are going to do the base case, and we're going to do n equal to 1 and 2. So base case, we verify for n equal to 1 and 2. We say, okay, let's verify. Let's assume we verified it and it worked out. Okay. Because n minus 1 over 2 floor is 0, so 2 to the 0 is 1. F of 1 is at least 1, and f of 2 is at least 1. That's verified. Yeah. And now, what about the induction hypothesis? Okay. Let's say that we know that for 2 of these it works. Right? For two of these. So let's say our induction hypothesis tells us it works for the previous 2. Right? So for 2 successive ones. That it works for n and n plus 1, which is 1, 2, 3. So these are always odd and even. So let's call it 2k plus 1 and 2k plus 2. So it's odd and even. So it holds for these 2. And now the step, we want to show it works for Is it nicer if I just make it 2k minus 1 and 2k? So it holds for 2k minus 1 and 2k. And now we are trying to show it holds for 2k plus 1 and 2k plus 2. Right? Is it clear what I'm doing? Yeah? Yeah? Given that it holds for these, holds for the next 2, holds for the next 2, holds for the next 2, and so on. Then it holds for all natural numbers. Okay? But why should it? Well, what we know is that from the induction hypothesis, we know that f of 2k minus 1 is at least 2 to the power of 2k minus 1 over 2 floor. And f of 2k is at least 2 to the power of k floor, 2k over 2 floor. Okay. Now, to show that it also holds for 2k plus 1, what do we say? Well, we say f of 2k plus 1 equal to f of 2k plus f of 2k minus 1, which is at least, by the induction hypothesis, 2 to the power of 2k minus 1 over 2 floor plus 2 to the power of 2k. over 2 floor. But remember, we were doing these in 2s where this over 2 floor is exactly the same as this over 2 floor. No, sorry, this is 2k minus 1 over 2 floor. Right? Sorry, I'm making some arithmetic mistakes, but what we wanted was n minus 1 over 2. So we wanted 2k minus 1 over 2. So that's 2k minus 2 over 2. And then we wanted 2k minus 1 over 2. But remember, when we take the floor of these two numbers, we get the same thing. Right? So what we're claiming is, remember, in both cases we got, when we subtracted off 1, we got 3 minus 1. That's when we got the even number, and we got that divided by 2. So the first one, this is where we got the even number. So this is 2 to the power of k minus 1 plus 2 to the power of k minus 1, which is equal to 2 to the k. Right? And what did we want to show? What we wanted to show was f of 2k plus 1. What we wanted to show is f of 2k plus 1 is at least 2 to the power of this number, 2k plus 1, minus 1 divided by 2 floor. So that cancels. That cancels. So what we wanted to show was it's at least 2 to the k. And that's exactly what we showed here. Right? So remember, I mean, this got a little complicated. It got a little out of hand in terms of complications. But then we also always have that picture to guide us. That's what we were doing there. Right? And then the fact was, we went through, we did the calculations, we got the correct bound. Therefore, by induction, we are done. Right? So we have something we are defining by recursion. How do we analyze it? Always by induction. Yes? I'm sorry?
I said, do you turn the 2 to the 2k minus 1 over 2 into 2 to the k minus 1? Because k minus 1 half of yours is just k minus 1.
Yeah. Okay.